Hello everyone, welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. I am currently working on a new project. I wish to build a more complex multimeter with an Arduino and needless to say, I'm working on various analogic circuits that will need to basically take the input voltages and measure currents as well and feed them into Arduino in order for the Arduino board to, do its job. Anyway, I still have work to do until I manage to have the full schematic done and then to produce the PCBs with components. However, as I'm designing it, I have stumbled on a certain problem that I needed to analyze, and I thought, why not make a video about it? Because it's not something that I've seen on YouTube, but it's a phenomenon that happens sometimes when we are using op-amps, and we might not be able to fully understand it, or we might not be aware of it, but it will definitely affect us. And the idea is that, well, op-amps are, needless to say, created from various transistors, right? And transistors have this thing called saturation, which is a state in which they can find themselves. And the saturation was described in other videos on other channels, so I'm not gonna get into it. And the usual working of a bipolar transistor or a field effect transistor. But the idea is that when transistor saturates, it apparently it tends to get stuck for a short while in that state, and if we want to switch it from being saturated into the linear region or back into blocking it, well, it's gonna take a bit of time. Not a lot, but sometimes it's significant. Now, we don't really bother all that much with this when we are actually using transistors in our circuits. However, since transistors at the base of op-amps, right? Because op-amps are made of transistors, especially bipolar transistors, then needless to say, this phenomenon happens for op-amps as well. So when a transistor inside an op-amp gets into saturation, it affects the workings of the op-amp himself. So we need to understand this in order to help prevent the op-amp from getting into saturation, because then it will behave in a way that we might not like. So before we actually get into this phenomenon, and I'm gonna explain it to you, I'm gonna show you what very simple experiment I've done and that everyone can do at home to basically test any op-amp. Let me make a small I don't know how you say it, when you remember things that you've learned in the past. Let me talk a little bit about what's called the input common mode voltage. It's something that other people have definitely spoken about in their videos on their channel, so I'm not gonna create a dedicated video for this unless, I don't know, several people ask me, but otherwise, you can definitely go on other channels, especially very good channels of electronics, and you will definitely find what it's all about. But I just want to recap quickly how we must see this and conceptualize this, right? So if we have an op-amp, and as with any op-amps, it needs two power rails, a rail that's denoted by V minus here and another rail denoted by V plus here. We have two inputs and typically one output. We're not going to discuss about special op-amps that are actually having two differential outputs, just the regular op-amp. Well, the idea is that the voltage that we must apply on either of the inputs must fall within a certain range of acceptable voltages, and the output that the op-amp is going to give us will also be within a certain range that the op-amp is able to provide on its output, right? So there are we're not going to focus a lot on the output because we don't care all that much, because what we do with the op-amp is mostly related to the signals that we send on the inputs. So that's where we need to be extra careful. We do need to be careful about what we're doing in the feedback circuit, because based on that, the output might go beyond or try to go beyond these limits, and that's going to be a problem, and I'm going to show it to you in the second half of this video. But for the moment, just to recap, when we are looking at the inputs, there are four potential situations in which we can find ourselves, right? So there are two limits, the one upper limit and one lower limit. I've symbolized them with green horizontal bars here, right? And they are typically, or how we need to conceptualize them, they are voltages that find themselves at a certain distance away from the power rails. So the minimum level is a certain distance away from the negative power rail. Therefore, on this limit, this limit is basically a voltage that is slightly higher than the negative power rail, and the positive limit is a voltage that is slightly lower than the positive power rail. Okay, and we can find ourselves in one of four potential cases. The first case, when we need to make sure that the input voltages stay within these two limits, okay, because both limits are important. So in other words, the voltages on the inputs must not go never ever below a certain threshold or above a certain positive threshold. And a good example of this would be the very old Micro A741 op-amp, which in the data sheets somewhere there's something called common mode input voltage range, and we see that for plus minus 15 volts. So if this is minus 15 and this is plus 15, then we see that this input voltage range is typically plus minus 13 volts. So these thresholds are basically around 2 volts apart from each power rail. So the positive, the inverting and the non-inverting inputs must never go closer to the positive or to the negative rail by 2 volts or more, or less, sorry. Okay, another case is when this lower limit, we still have the upper limit at some level relative to the positive rail. However, the lower limit is down at the negative rail. So on the input, we can have a voltage as close as 0 volts relative to the negative power rail. Okay, and this is a good example might be LM324 or 124, 224. It's an entire family of op-amps, right? And we can see this in two places. If we go at a certain page in this table where we have common mode input voltage range, we see that the values here are expressed from 0 to VCC minus 2. In our case, VCC being the positive power rail, okay? So this clearly tells us that we can have down to 0 volts on the inputs, but also if we go to the very first page, we can see something like common mode input voltage range includes ground, allowing direct sensing near ground. If we see something like this, then this is clearly what it's all about, so we don't even need to look in the table of the datasheet, okay? A similar situation happens in some other op-amps that have these two cases reversed. There are op-amps that allow you to have their input voltages up to the positive power rail, including the positive power rail, but they do not allow you to go down to 0, to the negative power rail. They require you to keep your input voltages away from the negative power rail by a certain amount. And a good example is Tele 070 something, or 060 something, or 080 something, where again we have this information basically written in two different places. For VCC plus minus 15 volts, we see common mode input voltage range is typically from some minus 12, or other words, around 3 volts away from the negative rail, all the way up to 15 volts, so including the positive power rail. Similarly, if we go to the first page, just like in LM324, we see this information written like common mode input voltage range includes VCC plus. And that's yet another clear sign. And the fourth case, we have what's called rail-to-rail input-output, which basically means that, well, actually, input-output, there are two separate things. Now we're concerned only about the inputs, so we have what's called rail-to-rail, and rail-to-rail essentially means that particular thing, either input or the output, or sometimes both, can go up to the positive and negative rails including. So we no longer have these thresholds in between, right? And a good example of this is microchip MCP 601 to 4. Again, it's an entire family of op-amps, and not just this one, but I picked this one because it was easy for me to pick. This information is written clearly on the first page, rail to rail, input, output. So both the input and the output can basically hit the power rails, okay? Now, it's important to know this because sometimes we will be violating both inputs and outputs and cause problems to the op-amp. Some other times we will be finding ourselves violating only one of these conditions. So in order to basically understand the phenomenon of saturation inside the op-amp, I've made myself a very simple circuit, non-inverting configuration, right? One of the simplest that there can be, with an amplification factor of 101, mathematically speaking, but for the sake of simplicity, let's just say 100. I'm applying a square wave input signal, and I'm taking a look at the output on oscilloscope. And I'm making it so that in the first case, I respect both inputs and outputs ranges of voltages. And in the second case, so basically I'm inputting a very small signal that even when amplified by 100 results in an output signal that is still within the boundaries of the op-amp that I'm using. And then in the second experiment, I'm essentially increasing the amplitude of the input signal so that the output will the op-amp will try to make its output go above these limits. Of course, he won't be able to do so, but that's when the op-amp will have certain transistors go into saturation and cause problems. Okay, and like I said, this is the circuit. I've used LM324 because this is what I had at hand. And these are the two experiments. So in the first case, I've put a plus minus 100 millivolt signal on the input. The entire circuit is powered by plus minus 15 volts. I forgot to mention that earlier. So if we multiply 100 millivolts by 100, we get 10 volts. So the op-amp will output plus minus 10 volts, which is within the range of acceptable voltages for the output of LM324 when we're having 15 volts, plus minus 15 volts differential power supply. And we see that with yellow the output signal, okay, and we see that both signals are synchronized with each other. So when the blue, the input signal, starts to rise quickly from minus 100 to plus 100 millivolts, that's when the output signal starts to increase as well. It doesn't increases anywhere near as fast because there's another parameter limiting the op-amp, which is the slew rate. I'm not going to be talking about that, that's a different topic. But essentially, due to the slew rate, the output will increase gradually. This is why we see this this yellow line that's not perfectly vertical. It's at a certain angle, but it's a straight line. That's a clear indication of the slew rate. But nevertheless, the point in which the output starts to increase is exactly the point in which the input voltage jumped from from the minimum value to the maximum value. And we see the same phenomenon happening again on the full edge of the input signal. The output signal also starts to decrease at the same time, again with a certain slope, but that's besides the point. The point is we have both signals in sync because the op-amp doesn't have any transistor into saturation. Now, if we increase the input signal so much that the output will be forced to go into saturation because the op-amp will want to output a value of a voltage that's not possible, and this is the case here. I have 500 millivolts per vertical division. I have about 3 divisions above and below ground, so about 1.5 plus minus 1.5 volts for the input voltage. If we multiply that by 100, we get that on the output, mathematically speaking, on the output we should have had plus minus 150 volts. Of course, that's not possible. First, because I have plus minus 15 volts power rails. Second, because the op-amp would not be able to work with 150 volts anyway. So the op-amp will try to make the output voltage as high and then as low as possible, but it will hit those rails, those limits, those output limits that he has on the output, and that cause him a problem. And this is where we get to see this effect of saturation, because here when the input signal rises from the minimum value to the maximum value, we see that instead of the output voltage starting to rise slowly, just like in the previous case, the output voltage remains at that minimum value for some 30 microseconds, and then, so it's basically like a delay, and then it starts to increase up until it gets to the maximum value. Okay, and then of course it stays at the absolute maximum value that it can potentially have, which is I think about 14 volts in this case. And then when the input voltage drops down to minimum, the op-amp is able to start at the same time is descent with the output voltage. So we don't have this phenomenon on the falling edge, but we do have it on the rising edge. And this can definitely be a problem in certain circumstances, in certain circuits. This delay is basically caused by the saturation of some transistors inside the op-amp. So this is definitely something we need to be aware of, and yeah, in some cases we need to do various tricks to our circuits to prevent this from happening. Otherwise we might have undesired effects going on in our circuit, and overall it will not work as expected. Okay, so this is it. This is what I wanted to show to you. I hope it was useful. It took me a while to understand it. I was trying to simulate some circuits, and I've had various problems. I just didn't understand why. And at some point in time I found this thing, so yeah, needless to say, I wanted to do some experiments, and why not show this to you as well. So thanks a lot for watching. I hope you found it useful and interesting. If you want to see more from my works, please hit the like button and consider subscribing to my channel. Also, there's a Patreon link in the description. If you want to benefit from my work even more in the future, please consider supporting my work on Patreon. Any help is welcomed. The faster I can get components and maybe even lab devices, the faster I can study electronics and come here to you and teach you all sorts of things. And also, the faster I will be able to potentially take requests as well and study something that you might be interested. So thanks again for watching. I hope to see you soon in a next video. Bye bye.